Guys, welcome to another short walkthrough example for Bellman Ford algorithm. So in this series, I'll be discussing Bellman Ford algorithm in a nutshell for a directed graph. And this example is also extracted from our Chinese tutorial video. But note that in this walkthrough, I'm using the approach from Michael Sambo. I'm not sure if I pronounce his name correctly, but I will link all the relevant videos here. Because if you prefer, you can follow the method from the original video author by Didi Chen. But I think that method is a bit confusing to me, so I try to adapt and try to adopt with Michael Sambo's method and source code. Everything I will link in the description down below, so don't worry, you can find that. So here we go. What is Bellman Ford algorithm? Bellman Ford algorithm is a non-greedy algorithm, unlike Dijkstra, right? It is used to find the shortest path from a single source node to all the other nodes in the graph. Yes, the way that it works is kind of similar like Dijkstra, but the only thing that is different is that in Bellman Ford, negative weights are allowed as long as it has no negative weight cycles, meaning the sum of all the weights in a cycle will give you a negative value instead of more than 0, okay? So in Bellman Ford, the maximum number of iterations will be v minus 1, where v is the number of vertex. Okay, so let's try this, and don't mind my my tone or my language right now because I'm filming this at midnight. So if I do make a mistake, please correct me in the comments. Comment down. Please comment below and notify me. All right. Okay. First, we pick a source, right? Source selected is 1. So I want to find the shortest distance from source to all these vertex. Okay, and this column will represent for each iteration. Okay, so let's do it. Okay, first, as usual, our default will be infinity, and our previous vertex will be none. If you're not sure what these are, you can refer to my Dijkstra video. Basically, when you first start, the distance between you and all the vertex should be infinity, but to you and yourself is 0, so it's 0. But this is what the default is, okay? And then everything is initialized to none. So my previous vertex should be myself, right? Or yeah, it's actually none. It's none. Okay. So let's start. So from vertex 1 to vertex 2 or vertex 1 to vertex 3, we will explore the outgoing edges. Remember, whenever we check the outgoing edges. So v1 to v2 is 8. So we update here. So our source is actually v1, yeah. So v1 to v2 is 8. v1 to v3 is 7. Okay, yeah. So v4 and v5, we can't actually explore based on the original video. But if I follow the Michael's method, okay, in his video he explained for each iteration you have to explore all possible nodes, outgoing edges. So I think that the original video's approach is something that confuses me. So I adopt Michael's approach. So for v3 to v4, okay, now v4 here, right? So for v4, before we even consider v4, we will go through horizontally. Since we already checked v1's possible edges, right? Now we go to v2. So now v2, we could either go our outgoing edges, we could go to 5 with a distance of 3. 8 plus 5 is 13. Sorry, my bad, it's 13. So we can write that down first, all right? And then we could also go from 2 to 4. Okay, 1, 2, 4. So it is 8 minus 4 is 4. Because why we update is because the value that we get earlier is actually smaller than infinity. That's why we update it. And then now 1, 2, and 3, 8 minus 2, 6. Okay, so originally we already have 7 as our shortest distance, but since 6 is smaller than 7, we will put here. And remember when we track our previous vertex, if you could recall, my bad for not updating earlier. If you could recall, our previous vertex for here is none. v2 here is from v1. Remember? Okay, and then v3 here is from v2. Because originally it was 7, right? So our original previous vertex was v1. It starts from v1. But now since we are coming from 1, 2, 3 here, vertex 1, 2, 3, so our previous vertex is actually 2. So we will put 2 here. v2, my bad. Okay, and then for v4, again, since we're from here, we will also put v2. And this is also v2. Okay, so we have finished exploring v2 for the first iteration. Now we'll move on to v3. It's still in the first iteration. So for v3, we have 2 outgoing edges, 3 to 5 and 3 to 4. So v3 I already have distance of 6. So 6 minus 3 to vertex 5, I will get what? I will get 3, right? So I will get 3. Because 6, originally I'm from v2, 8 minus 2 is 6, 6 and minus 3, we'll get 3. We will update it because 3 is less than 13. Okay, so we will update here 3, and our previous vertex is v3. And now let's explore vertex 4 from vertex 3. So vertex 3 to vertex 4, you will have 9, isn't it? So from vertex 3, we originally have 6. So when we add 9 to it, we'll get 6 plus 9 is 15, and 15 is greater than 4, the original shortest distance from source to v4, so we don't update it. All right. So we have done exploring vertex 3. Now moving to vertex 4. The only way we can explore is the outgoing edge is through vertex 5. So from vertex 4, we already have a distance of 4. So when we go to vertex 5, 4 minus 10 will be negative 6. Oops, my bad, negative 6. And our previous vertex is vertex 4. So we have done the first iteration of the Bellman fold algorithm. So next, when we move on to the second one, we are essentially repeating the same steps. Okay, in the original video, they divided into different steps because they did not finish exploring all the nodes in one iteration. That's why you'll notice that my approach is different, because my approach, I'm following the video of the 5 minutes algorithm Bellman fold explained by Michael. So that's why it's a little bit different. So moving on to the second iteration, it's still the same thing. You're still essentially checking from each vertex. You're repeating the same steps. Here, here, and then the outgoing edges, 3, here, here, and here. You look at my cursor here. Oh, by the way, this is what we are exploring. Oh, by the way, during the first iteration, I forgot to check for vertex 5, but since vertex 5 has no outgoing edges, so we don't have to check for it, okay? But by default, you have to check for it, but if you don't have any outgoing vertex, so it's fine, okay? Now we're moving on to the second iteration. It's still the same thing. It's still the same thing. So you're doing the checking again. Do this, like if you notice my cursor earlier, it's the same thing. So you notice that actually the second iteration and the first iteration, the result will be the same if you do it yourself. So in a more optimal Bellman fold algorithm, you terminate earlier. So you check like if update here, if there is update, we will continue the next iteration. And if the next iteration has the same thing, our update will become false. We will break out of the loop. So therefore, we don't have to run v minus 1 iterations because this is the max. By default, Bellman fold will run v minus 1. But if you do early termination, it will only run 2 iterations. So yeah, I hope that's clear. Yeah, this is the original version of video in Chinese. You see there's slight differences, but I prefer this method actually because it's more clearer. And then moving on, I also want to mention about negative weight cycle. If you notice, right, I also extracted this from a video. I'm going to link everything down. So from this picture, it actually shows that this is a cycle, right? You see the arrow, and we have v number of nodes, so it's 3, and our maximum number of iterations if we were to perform Bellman fold would be 2, because v minus 1 is 3 minus 1 is 2. And then to check if we if you want to detect cycles, right, we can check if we can perform the third iteration of edge relaxation, like exploring. If somehow it still managed to update the distance, because maximum by default we can only do 2, but somehow if you do the third one and it still updates the distance, it means that the negative weight cycle is true. So the Bellman fold algorithm fails. Okay, for more details, you can look at this video, and maybe I will upload a updated version of this video again in the future. But basically, you're going through the same thing. You're exploring the same thing, like the same steps. You'll notice that you'll keep distance that you update, you'll keep continuing, like it's always gonna be negative, and you'll never stop. So there's a cycle. That's how you detect it. So yeah, in the next video, I'm gonna discuss about Floyd-Warshall, also using Michael's video as an example walkthrough. However, maybe I'll adopt with another approach, like maybe from other YouTube or my approach. So stay tuned for that. So that's all for today. Thanks for watching. I hope it's clear. And if I do make any mistake, please feel free to correct me in the comments. And I'll leave all the links in the description below. Thank you.